With the release of ASAP 2008 come several significant enhancements in the area of optimization. ASAP has always included optimization capabilities for both imaging as well as non-imaging systems, but the new optimization capabilities include a platform that includes several new optimization techniques. These include a Brent's method, a downhill simplex technique, as well as a simulated annealing technique. Each user will be allowed to select the appropriate optimization technique for any given imaging or non-imaging design problem. These new tools are in addition to the optimization capabilities already within ASAP. In particular, we have added 3 new tools, one based on a Brent's method optimization technique. Brent's method is the tool that is appropriate if you have an optimization which only includes one single variable. Also available will be a downhill simplex method. The downhill simplex method is appropriate if you have multiple variables, but you have a relatively smooth solution space. Simulated annealing is available for, again, multiple variable optimization, but for those situations where you have a much more complex and possibly even discontinuous solution space. Let's take a look at a simple example. In this particular case, I've defined a surface that is a parabola. However, I want a parabola that has a focal point at this location. What we're going to do is allow ASAP to optimize on the coefficient of the parabola in order to form an image at the proper location. To do this within the new optimizer, what I'll need to do is simply come up and select under the editor menu, Optimize Script, and as you see, a tab dialog box opens up that will allow me to define my design variables, my design objectives, any objective constraints, as well as exit criteria, and to select the appropriate optimization method. Let's start by defining our design variable, and it's simply the coefficient A. So I'm just going to right-click on that and select Define Design Variable. And I see the name of my variable. I could also give it an alias if I wanted, and the nominal value. With the Brent's method, it's best to set a minimum and maximum value, and because I know the orientation of my parabola, I know that my coefficients will not be negative or below 0, so my minimum value will be 0, and my maximum value we can set to 1. I could also set a step size. I could also set a limitation on the step size based on manufacturing tolerances. For this example, those won't be necessary. The next thing I want to do is define my merit function, which is my design criteria, and this is simply I want a minimum RMS spot size, which I've written into my ASAP script file, and I'm simply going to select this and define design objective. In my objective table, I can set any target value. In this case, I do want the target to be 0. I could also define weighting factors for my different constraints or targets, but since I only have the one constraint, I will just leave the objective weight as 1. I have no additional constraints in the system. The exit criteria page will allow me to define when I want ASAP to stop the optimization. Because global solution space is infinitely large, in theory the optimization could proceed forever. That, of course, is not reasonable. So at a minimum, you need to set a limit on the number of trials. You can also set a value based on how close to your merit function you need it to be, what the divergence limit is. In other words, if the optimization seems to be taking a wrong path, you can tell ASAP to stop the optimization, or you can limit it based on how much noise. In other words, as the solutions get smaller and smaller and smaller, but approximately equal to each other, when do we stop the optimization? I'm just going to leave a limit on the number of trial solutions at 100. And then we can select the optimization method as well as give a name to our optimization file. What this will do is allow us to save as a text file the result of each and every iteration, and we can analyze that in some program external to ASAP, or we can simply look through the data visually at the end. Since I only have one variable, the only optimization technique available to me is the Brent's method, so all I need to do is click the Start Optimization tab. And as you can see, ASAP is making significant changes to the shape of our surface. And after it does a few iterations, it will start giving us a table of the solutions. And as you can see, in a very small number of cycles, we've probably reached the optimal solution where the RMS spot size is effectively 0. ASAP will iterate through this several cycles, and then when it determines based on the repeatability of the measurement that it's not changing, it will cancel out of the measurement. As it's done at this point. So it's decided that this is the optimal value. Now what I can do is choose to save this result. So if I open my file back up, you'll notice that I have, for each of my trials, I have my figure of merit, I have the value associated with the variable at that particular time, and I have the value associated with my constraint. And my figure of merit is simply the sum of the squares of all of my design objectives. If I want to analyze one of these systems specifically, let's assume I want to look at system number 12, I can come up into my ASAP menu bar, and I now have an option of Optimize, and from Optimize I can select the option to save the system under evaluation, and this will save system number 12 for me. And I'm just going to give this file a new name and save that. And as you can see, that file is now available to me in my input window. So now we'll close the optimization. And yes, we want to end this session. And I'm going to go back and get my original file, or that I just saved, and you'll notice that the value of the variable has been changed to that determined by the optimization. And now I'll run this file. And we see that indeed we now have the proper shape to have the parabola of the appropriate focal length. The next example we're going to look at will use the downhill simplex method of optimization. What we're going to look at here is something very similar to our prior example. We're going to use the ASAP general surface again, but this time we're going to add one more coefficient, the coefficient on the x squared y squared term. The design goal of this system is to create a square illumination pattern on a viewing screen using rotationally symmetric or circular optics. In this particular case, we've got the system geometry defined using the ASAP general surface, and the x squared and the y squared coefficient will be similar, just as they were in the parabola, and what we have here is an offset term to that parabolic shape. Now there are several ways we could optimize this system. We could create an extended source and trace a large number of rays and attempt to minimize the variation across the pixels of our detector, but in reality a simpler way is to simply map a circular distribution onto a square, and that's what I've done with this particular ray set. What I'm doing is tracing rays that start at the edges of a circle and at a medial circle in one quadrant of our design, and then I'm simply going to target those to the appropriate corner values within our square image space. And as far as my merit function is concerned, I'm simply going to grab all of the information about those rays and compare them to my desired values. So to do this optimization within ASAP, I'll need to simply go under Editor and select Optimize Script and define my variables. Let me move this out of the way for a moment. And these are my variables. After I've defined the variables, I can add constraints. Not always necessary, however, if any time you can restrict the solution space ASAP needs to search, it will make the process much more efficient and therefore faster. So in this particular case, I know the shape or the orientation of my surface, so I can set this to a minimum of 0 and let's say a maximum of 1. And for my departure coefficient, I might not know the shape, but I know it will be significantly smaller than my power coefficient. So let's put a range from minus 0.1 to plus 0.1. I'm not going to worry about the step size. I'll let ASAP decide that as appropriate. Now what I'll need to do is also tell ASAP about all of the terms within my merit function. And these are terms related to the total flux on the detector, as well as calculating the location of each of those individual rays on my image surface. So I'll need to make each of these design objectives. So I will just select each one by right mouse clicking and selecting design objective in sequence. And now I have all of my design objectives listed. There are no other objective constraints necessary in this system. My exit criteria, I'll again simply leave at the number of trial solutions. If ASAP hasn't found a solution within 100 trials, I might come in and make modifications. The last thing I need to do is to select the optimization method. In this case, because I have multiple variables, I can use either downhill simplex or simulated annealing. In this particular case, I'm going to choose the downhill simplex because I do have a very smoothly varying solution space. Under the downhill simplex, you'll see that I have options available to me. In the downhill simplex method, what ASAP will do is form a simplex based on your number of variables. Since I have 2 variables, ASAP will form a simplex that has n plus 1 or 3 points, so triangles, located within a plane. As ASAP analyzes the value of the function at the 3 vertex points of the triangle, it will then flop over, expand, or contract the triangle in an attempt to find 3 vertex points that have better merit function values than the current set of vertex points. These features here allow you to modify how ASAP finds the next simplex shape and orientation. I'm going to stay with the defaults for now because these are selected to give the best balance in the optimization. But again, by adjusting these features, you can allow ASAP to search more broadly or more narrowly within your total defined solution space. So again, let me just click the Start Optimization button. After clicking the Start Optimization button, ASAP will initially investigate the location and solution space of the current solution, and we'll look at adjusting the different parameter values. And then it will start displaying the results of each of the trial iterations. What's being graphed is the figure of merit for each of the trial solutions, and the figure of merit is simply the sum of the weighted squares of all of the optimization operands. You'll notice that some of the trial solutions actually result in a slightly degraded merit function, and ASAP doesn't hide these solutions. ASAP shows you all of the paths that the trial optimization takes and allows you to analyze this data externally to ASAP, which will give you a better idea of the shape of your solution space. But you'll notice it doesn't take very long for ASAP to start determining what the appropriate downhill path is to get to a local minima, and we will proceed until we reach that conclusion. And after our 50 cycles, the optimization comes to a halt. And as you can see, the system found the region of an optimal solution quite a while ago, and it just has iterated around there. Solution space is somewhat rough with just these 6 rays, so it's just basically found the location of the local minima, and the slight differences between these different solutions really won't matter. So what we can do now is take a look at one of the solutions in particular, and it doesn't matter which one, and I'm simply going to highlight one of the files in my optimization results dialog box, and I'm going to, on the Optimize menu, select to save the system under evaluation, And I'm just going to call this number 49 since that's the trial number. You can select any name that you'd like and just click the Save button, and you'll notice that this file is now available to you in your INR input menu. Now what we need to do is just close the optimization, so I'm bringing back the optimization setup summary and clicking Close. And yes, we do want to terminate this session. Information about all of the trials has been saved as a text file in your working directory, so you can do other analysis or post-processing, or even look at several of the different solutions just by opening that text file. But here's the solution I selected, and here are the variable values that were the result of that trial. And now let's just run the analysis. And of course, this doesn't show us very much other than our surface, which is very, very small relative to our detector. But I have a couple of other files here. What we're going to look at now is simply on a detector where those 6 specific rays are landing. So let me just run this file. And on a very coarsely sampled array, here's where all of the rays land. You'll notice that central ray didn't quite make it to the center, but the rest are very, very close to the targeted position. But of course, this is simply for several rays coming from a point source. What we also might want to look at is what's the distribution of energy on our detector surface from an extended energy distribution. And I have another file that will do this here with a randomized distribution of rays. So what we'll first do is get rid of those 6 rays and then launch a randomized grid of rays and take a look at the output. And you'll notice at our detector location, we have a very uniform square distribution of energy. The key of this example was to show you that sometimes it's more important to determine what a smart and effective merit function is. If we had traced a very, very large number of rays, such as we see right here, we would have reached the same solution, but it obviously would have taken a great deal of time. If we develop merit functions that are more efficient, simply by tracing a few rays in this example, you'll be able to get an optimized solution in a very short period of time. The third type of optimization available is simulated annealing. Simulated annealing is appropriate for those situations where you, for instance, might not have a continuous solution space, or you might have to search over a very large solution space to try to find the answer. What we're going to look at in this case is a problem where we're going to optimize for fiber coupling efficiency. But in this particular case, rather than having something like a simple point source, we actually have a directionally apodized energy distribution. I want to show you what the energy distribution looks like so you can see the complexity of the problem we're solving. So I'm going to simply show you what the rays look like coming from our source in a direction cosine space. And as you can see from our apodization profile here, most of the energy is directed towards an angle of 25 degrees, and then it tapers off from there, and there's no energy beyond 50 degrees, giving us basically a donut-shaped distribution. If you wonder why we might use something like this, this is very representative of the output from something like a VCSEL. So here in a somewhat granulated picture shows what the energy distribution looks like. Again, it is in no way uniform. It is very, very directional and very specifically directionally apodized. The simulated annealing is a tool that is absolutely perfect for this type of optimization. So let's take a look at the design we're going to optimize, and it's simply a light pipe. And what we're going to do is use this source, but in the light pipe what we're going to do is shape the spherical or conic coupling lens. In this particular case, we're going to optimize on the radius and the conic constant, so we'll have a simple conic shape to the surface. And what we want to do is find the optimal solution for a particular source location. We'll start simply by defining our variables and setting any ranges on those variables, as well as our merit function. In this particular case, we also will have some graphical information that we've wanted to see during the analysis, but for the optimization, it will proceed significantly faster if we comment out the graphical output information. Everything else will still be fine, and then we'll see the final result. And now we'll set up our script for optimization. Let's go under Tools, Optimize Script, And let's select each of our variables and then right-click to add them to the design variable table, and select the conic constant as well, and also make that a variable. Now I want to set a minimum and maximum range, so I want this to remain the proper orientation, but I know it's not going to be any bigger than 0.4, and obviously it will probably be significantly less. And my conic, I want to keep this somewhere between an ellipse and a hyperbola. There are a wide range of families of solutions for this problem, but I will restrict my solution space to conic constants being no smaller, no more negative than -3, and to be a negative value. And those are the only constraints I'm going to put on my variables at this time. And now I need to define my design objective. In this particular case, it's simply the fiber coupling efficiency, or the throughput. So I'm going to highlight that row in my file and simply right-click and select Define Design Objective. And here's my throughput. I'm going to target it to 0, the weighting factor of 1, because I'm only going to have this one optimization objective, so there's no need to adjust the weighting factor. I'm going to set my exit criteria to 50 cycles. And I'm going to select my optimization method of simulated annealing. With simulated annealing, we need to set an initial temperature, and this basically defines the range of solution space that ASAP will search over. After a given number of cycles, ASAP will automatically contract or lower the temperature to bring in the scale of solution space. You do need to enter an initial temperature. If you set the initial temperature to 0, you are effectively simply doing downhill simplex optimization. I'm going to set my initial temperature to 1, and I'm also going to use a power law truncation or changing of the temperature value. And this simply sets the exponential power of the temperature contraction, and the power block indicates how frequently the temperature will be adjusted. In this case, every 10 cycles, ASAP will adjust the temperature. And we'll just simply click on the Start Optimization button, and we'll look at the results. What you'll notice with the simulated annealing is initially ASAP will take broad swings in the merit functions of the different trial solutions. The hotter the temperature, if you will, the more likely ASAP is to select or accept a solution that results in a significantly degraded merit function. As the temperature gets lower and lower, ASAP becomes less willing to accept those solutions, and then finally, towards the end, only trial solutions that result in an improved merit function will be accepted. And as you can see, the optimizer seems to be reaching into a reasonable level of solution space quite rapidly. And after ASAP has processed the requisite number of trials, the optimization will come to a halt. And as you can see, that ASAP was able to find several solutions around a particular maximum coupling efficiency. And again, this is simply because there are a wide range of conic curves, combinations of radius and conic terms that would give us approximately the same solution. Again, we're going to save one of the solutions and just take a look at it. And I will just select, well, for example, this file right here. And again, under Optimize, select Save the System Under Evaluation, or SU, and just give it a distinct name and click the Save button. And you'll notice that this file is now available to you in your input INR script list. So we'll simply stop the optimization by opening the optimization setup summary and click the Close button, and yes. Again, information on all of the trial solutions has been saved into your working directory as a text file, so you'll be able to do any other analysis or post-processing or look at several different solutions if you'd like. But we'll just run this solution, and here are the radius and conic terms that ASAP determined for this particular trial. And I'm just going to run the file. And if we look at the command output window, We see that in this particular case, the coupling efficiency is approximately 87%. And now what we've looked at were 3 different example files that demonstrated the different optimization algorithms available to you with the new optimization capabilities of ASAP 2008.